Welcome back, ladies and gentlemen. Imagine a sound source, say a car's engine and exhaust, the noises that a car usually makes. Well, the sound waves are emanating from the source, sort of in all directions. So what I can do is I can try to represent, if we just take that location to be the general center of things, then we can say that, well, all right, we have sound waves. And sound waves are going to emanate in all directions. So I can kind of get this going. Yeah, don't move it. And so there's that guy, and we'll have sound wave there, and we'll have sound wave there. Okay, so you get the idea. Sound waves emanate in all directions from the source. And what's cool about representing the waves like this is we can sort of think of this as sound waves where these lines are, where these circles are, as being crests, or where we have those compressions, right? Where the molecules in the air are compressed more densely, and then in between, where in between the circles we would have the rarefaction, right? So it's kind of like a segment of a circle there, segment of a circle there, here and here, and in between the rarefaction. It's, remember, analogous to the crest trough pattern for transverse waves, but here these are longitudinal. So well, what about this, you say? Okay, the sound waves move outward in all directions. The wavelength between the crests can be shown very easily. We can say, well, there is a physical length there from one compression to the next. And when we have that, we say, well, that's a wavelength. The symbol is lambda. Cool. And an observer that would detect the sound, the observer would say, you know what, let's say we have someone observing over here. The waves reach that person, they would say, you know what, I recognize this sound. And the observer detects the sounds with their normal wavelengths, and therefore the normal frequencies. The thing about this is, we have sound moving at a certain speed. These waves are moving at speeds toward the observer. And so there is this speed of the wave as it gets to the observer. There is a certain wavelength that the observer is experiencing, so to speak. And excuse me, to complete this relationship, what really happens is the observer hears a certain pitch in the sound, a certain frequency. And that comes from this relationship that is true of all waves. Speed of the wave is equal to wavelength times frequency. Cool. And so recall also that the speed of the wave, it really does not depend on these other two quantities. It is related to them, to be certain, but the speed of the wave depends on the properties of the medium. In other words, the properties of the air it's passing through, in this case. Awesome. But now suppose the car is moving, right? And it will always be closer. This is an interesting thing. The car, as it moves, will always be closer to the leading edges of its sound waves than it is to the trailing edges of those sound waves. How would that look? So here the car was stationary, and this guy is standing here, and he hears the sound. And he says, I detect a frequency. And that comes about from the speed of the waves and the wavelengths as this observer experiences them. What if, though, the car is moving? Here we go. Let's see if we can draw this. We have some ground, and we have a moving car, and moving fast. Right? There we go. My wonderful artistic skills. Now, what's the deal? Okay, the deal is this. It's hard to draw this on paper and represent it accurately. Here's why. I cannot draw all of these circles representing these sound waves with the same center. Because a sound wave that was made a few moments ago, like this one, has had time to spread outward from the source. This one was created when the car is here. But the next one was created some moments later, and in that time the car moved. So I have to put the center of that circle over here somewhere. Then some moments later, this sound wave is created and the car has moved, and I have to put the center of that circle further forward. And so this is going to be kind of interesting. I have to actually work backward a little bit. Let's see if I can do this for you. Now, start it like this, and okay, right here it's going to be making a small wave. Let me do it this way instead. I'm thinking it's probably this guy. Okay, there's the most recent sound wave. Now to make the next one, I have to move this back, so to speak. And I'll make the next one. Yeah, come on, paper. Don't turn. Okay. And then to make the next one, I have to go back even further. And let's put it about there. Make sure I'm not going too high with it. And there we go. Something like that. All right. And if I don't get in my own way. Okay, so check this out. A little incomplete circle here. Don't worry about that. Now, we can see, in effect, the statement I've just made. Let me reread it for you. The car will always be closer to the leading edges of the waves. These are leading edges of the waves. Than it is to the trailing edges of the waves. So the car is closer to the leading edge of that wave than it is to the trailing edge of that wave. This wave was created when the car was centered here, and it moved outward from that location in all directions. Outward in all directions. This wave was made when the car was centered here, and from that location it moved outward in all directions. This smallest circle, this wave, this compression, was made as the car is here, and it moved outward in all directions. Okay. So there's something interesting going on, quite a bit in fact. So check this out. We can identify pretty easily a couple things going on. Say first, we have a velocity of the car. And the car is the source, so I'm going to call that velocity the source of the sound. S for source. So what this has done is the wavelengths in front, that distance there, is different than the wavelength behind. So there's wavelength behind the car, here's wavelength in front of the car. And here's the deal. What if there's an observer in front of the car, over here? Yay, I'm observing sound waves, I can hear them. So the observer in front of the car receives compressed wavelengths. These wavelengths, as they get to the observer, are shorter than they used to be because of the car's motion. They're compressed wavelengths. So this observer detects a higher frequency. So think about this for just a moment. Because of this relationship right here, the speed of the wave does not change. Don't get confused between your velocities. That's why I labeled this different. This is the velocity or speed of the wave. It's set. It's stuck at about 343 meters per second. And that depends on the air. Well, now this observer is detecting a smaller wavelength, right? So we have a teeny tiny wavelength right there. So to equate to the same speed of the wave with a smaller wavelength, there must be a larger frequency there, a higher frequency. So this observer is going to detect a higher pitch sound coming from the car as the car moves toward them. Awesome. Well, what about an observer behind the car? Or we could say, as the car passes this person and now is moving away from them, as shown here. Let's ignore that now. Okay, so what's the deal? Well, the observer behind the car receives lengthened wavelengths or stretched wavelengths, and so detects a lower frequency, so it works just the same. The speed of the sound waves is the same, but they detect these waves to have longer wavelengths, sort of artificially lengthened, right? What that means is they detect a smaller frequency or a lower frequency or lower pitch. So as the car drives by, you hear the change in pitch. Okay, and it's in movies and TV shows all over the place, maybe even cartoons, and in real life it's evident all around you. I know you've heard it before. You just may not have recognized it for what it is. Now we see. Okay, did the sounds produced by the car change? Well, no, but the locations of the productions of those sounds affected the wavelength. Wavelength in front is compressed, wavelength behind is stretched. And that affects the frequency detected in front or behind that source of the sound. Aha! We're talking about Doppler effect. This is a Doppler shift of the sound. Okay, so there's some statements we can make about this. Some important things to write down, kind of brief. So kind of a summary of what we have so far. Summary statements. Here we go. When the source of a sound moves toward an observer, the frequency, I'll just put F for frequency, detected is higher. And so what that means is we could say, well, it's a higher pitch sound to our ears. While when the source moves away from an observer. Well, it's just the opposite. The frequency detected is lower.
Perla Burgos, please report to the counseling office. Perla Burgos, to the counseling office, please.
Little announcement there to break things up. So, summary statement, right? And we've seen that. Now we have a moving source and stationary detector. Detector in front, higher frequency or higher pitch. Detector behind, smaller frequency or lower pitch. Okie dokie. Well, I'm going to leave this space. I'm going to come back to that because there's another statement we'll write in just a few minutes. So now, well, that's all well and good. But what if the observer is moving, right? We have the ground, and there's this car just sitting there idling. Maybe now it's an SUV. Look at that. But the car is stationary. Oh, now the person who is observing, is some way moving. Well, let's put this observer moving toward the source of the sound. So we have velocity of the observer there, not initial velocity. So again, don't get confused. Different context here. This is just velocity of O for observer. This source of the sound is producing sound waves. Let's draw a few of those in real quick. And we're going to say centered right about there. Okay, so we can go 1, and we can go 2, and we can go 3, and let's do one more. Okay, that's really all we need to do. So what do we have? We have wavelengths here. And now this time, look at those wavelengths. Would they be any different behind the vehicle? No, they wouldn't. The vehicle is not moving. So those wavelengths would be the same on all sides. You'd have this other wave here, and that wavelength would be the same as this wavelength in front. But the observer is moving. So check this out. Here's the kicker. Okay. To the observer, that is moving toward the source. The sound waves seem to have a higher velocity. So the waves themselves have a speed this way toward the observer. The observer has a speed that way. So to the observer, those waves seem to be going faster than normal. So with a higher velocity, but they have the same wavelength. So again, we're back to this relationship. Okay, but they have, according to this person, a bigger velocity, but the same wavelength. So to accomplish that, what must happen to the frequency this observer detects? So the frequency must get larger to produce that relative increase in the velocity. I say relative because it's just relative to this guy. This guy thinks those sound waves are moving at him faster, him or her. Okay, and this observer is moving toward the source, and I guess that kind of makes sense, right? But what about an observer moving away from the source? So let's put someone here. Oh yeah, I don't like your car. I'm going away. I'm going the other way. There. Velocity of the observer moving away. To this observer moving away, the sound waves seem to be reaching him or her with a lower velocity. It's almost like taking that speed, take away this speed, gives you the speed this person sort of sees. Now, so with that lower velocity, from that same relationship here, here's our basic beginning, right? From that, with a smaller velocity, yet with an identical wavelength. Wavelength hasn't changed. It's normal. To produce a smaller velocity, this person is detecting a smaller frequency. Okay. So frequency detected is lower. So now I'm going to go back to my summary statements. I have another one to write. There we go. When an observer is moving toward the source, the frequency detected is higher. That right there sounds a lot like when the source is moving toward the observer, the frequency detected is higher, but it's for a different reason. Okay, now conversely here, on the other hand, how's that? When the observer is moving away from the source, comma, the frequency detected is lower. Okay, I normally don't try to write a lot, but this is kind of, in the videos, I mean, this is kind of important. It's sort of similar in the effect that is produced. When they get closer together, frequency detected is higher. When they move further apart, frequency detected is lower. Here, when the observer moves toward the source, so they get closer together, frequency detected is higher. When they move apart, they move away from each other, frequency detected is lower. The effects are similar. They happen for different reasons. Keep in mind, with a stationary source, wavelength is not affected, but apparent velocity is, and so that affects frequency. Here, with a moving source, wavelength is affected, but velocity of the waves is not. So because you're affecting the wavelength, you must be affecting frequency. All right, well, we got to put this all together. So here it comes. The world-famous Doppler effect equation. Can you handle it? Here we go. Your book does this differently, by the way. It depends on what source you look at. If you check out different textbooks or different websites, I have what I think is a pretty easy way of doing this. Doppler effect equation. Here we go. Frequency detected. Right there. Frequency detected is equal to frequency produced by the source, so the original frequency produced by the source, times some factor that changes things. And here we go. Here's where it gets interesting. V minus VO divided by V minus Vs. With no subscript, that velocity is the velocity of the sound wave. And we see it twice. Okay. VO is not initial. Remember, that's velocity of the observer. And Vs is velocity of the source. So we, in one equation, we can use a stationary source, that becomes 0, but moving observer. Or we can use a stationary observer, that becomes 0, but moving source. Or we can have both. Both of them could be moving. Here is the one rule. There's only one rule that you must follow with using this equation. And it is this. In terms of direction of your coordinate system, the one rule is from source to observer is positive. Always. Always. If you're using this equation, the direction, whatever the direction is, the direction that goes from source toward observer, is the positive direction. That is the only way this equation works. Okay, so we've got to remember this. You've got to follow this rule, or else solving problems doesn't work out for you. You end up not getting the right answer. So imagine this. If I set up some sort of speaker, and it's creating sound waves headed that way, and there's someone listening over here, yeah, rocking out, man, groovy tunes. So look at this. We have from source to detector would be the positive direction. That's what matters. Well, let's make it more interesting. Let's actually create a Doppler effect situation. We have the groovy tunes emanating from a car. And the car is zipping away from an observer. Aha. So look at this. In this situation, the positive direction is from source to observer, but what about the velocity of the car? The velocity of the car is this way, velocity of the source. That means the velocity of the source is a negative value. And velocity of source with a negative value, take away a negative, the denominator gets larger, the overall value gets smaller, and a frequency detected is lower. Aha, does that jive with our summary statements? Yes, it does. Yes, it does. This equation totally works. You need to know one equation and one rule to follow in terms of a coordinate system. And it works for all situations. Oh, by the way, it works for things beyond sound waves. Sound waves are Doppler shifted. It's true. And in fact, in a physics class, if you are using any kind of ultrasonic rangefinder, it is using Doppler effect to its advantage to give you a velocity of an object that might be moving. But it isn't just sound waves that use this. It works for light waves also. A cop's radar gun uses certain radio frequencies, and it gets a speed of your car by looking at the Doppler shift of those frequencies. Astronomy uses Doppler shift. It's kind of foundational to a lot of the work being done in modern astronomy. If you want to try to tell whether a distant star or galaxy is moving toward us or away from us, you look at its red shift or blue shift, and those are shifts in the frequencies of light. But frequency of light corresponds to the color of the light. So you see a change in the color, you wouldn't actually see it with your naked eyes most of the time. You would have to look at some sensory data, sensors gathering the light for you. But it works out, and it's the exact same principle, whether it's for light waves or sound waves. or water waves or seismic waves. Same principle. Doppler effect works absolutely, and it's beautiful. That's it for now. Thank you for watching. I'll catch you next time.